Okay, let's go ahead and get started. So today is very exciting. This is sort of the pinnacle of our discussion of Yang-Mills theory. So what I'm going to do today is describe the computation of the beta function that describes the running of the coupling constant with energy in Yang-Mills theory. And as advertised yesterday, we'll reproduce 't Hooft's famous computation showing that in some Yang-Mills theories, and in particular in QCD, which is the theory of strong interactions, the coupling constant actually becomes small and the theory becomes weakly coupled at very high energies. Roughly speaking, as we described yesterday, this is because in Yang-Mills theory, the gauge bosons have a sort of anti-screening rather than a screening effect, so that if you study the effective charge of if you have some fixed bare charge and you want to study the effective charge at long distance, rather than that charge being screened by, say, electron-positron pairs, which would make the charge weaker at long distances, in Yang-Mills theories, we'll discover that the charge can become stronger at long distances rather than weaker. Okay. And this is, at first sight, a bit counterintuitive, although if you want to understand just a little bit more physically how it is particles can anti-screen rather than screen, there's actually a nice discussion in Peskin and Schroeder, which has some references to the original literature that you could look at. I think it's somewhere in chapter 16 or 17 of Peskin and Schroeder. But today what we're going to do is a more direct computation of the beta function, just a direct calculation. And we'll do it using the language of Feynman diagrams, of course. So what we want to do is we want to consider Yang-Mills theory and in fact, so far we've considered Yang-Mills theory coupled to a fermion, transforming in some representation of the gauge group. In fact, what I'd like to do is consider something that's only epsilon more complicated. What I'd like to do is consider a theory where I have some number nf fermions, all transforming in a given representation R of the gauge group. So I suppose if I wanted to be really pedantic, I could say that I have a representation which is reducible and is n copies of a given irreducible, or nf copies of a given irreducible representation. Here, the representation, so here I'm just writing that a slightly different way, where I'm saying I have nf fermions all transforming in the same representation. Now, this is a useful example to consider because it is, in fact, the theory of nature. In the theory of nature, in the theory of QCD, the gauge group is SU3. The quarks transform the fundamental three-dimensional representation of SU3, and there are three generations of quark. So here, this NF reflects the fact that there are different generations of quarks. What we'd like to do, so last time we described the various ingredients in the calculation of Feynman diagrams in this theory. And in particular, I worked in a general gauge. But of course, as in the case of electromagnetism, the computations are easiest in Feynman gauge. So let me just remind you of what the Feynman rules look like in this gauge. Now, of course, the full computation of the beta function is rather involved. It's a somewhat lengthy computation. Many bits and pieces of it are computations that we've done before when we studied the one-loop structure of quantum electrodynamics. So gauge theory is just a generalization of quantum electrodynamics to a slightly more complicated set of gauge bosons than the photon, and a slightly more complicated set of matter fields. Okay? So rather than trying to go through the computation in complete mind-numbing detail with every index and every calculation, instead what I'd like to do is set up the calculation for you and go over some of the main points. And in particular, I'll borrow some results that we already worked out when we computed things like one-loop effects in quantum electrodynamics, and just describe to you briefly how these are changed to reflect the fact that we're in a gauge theory. So The propagator in Feynman gauge is very similar to the propagator of a photon. It's just g mu nu over k squared. There's only these other two indices which reflect the fact that there are d different species of gauge boson labeled by an index that I've called A and B here. And there's a delta AB which reflects the fact that the propagator is just completely diagonal in that index. You have an F, the kinetic term is d mu A nu A minus d nu A mu A contracted with the same thing with all of the indices raised. So there's an A index contracted with an A index, so there's a delta AB here. Okay. The thing that's different between electromagnetism and Yang-Mills theory, however, is that now the gauge bosons interact with one another. So for example, there's a process where two gauge bosons can split to form a third. So I'll just briefly remind you of what the, sorry, that's supposed to be a P, of what the Feynman rules look like. So here, this is the 3-point function vertex. This is proportional to the gauge coupling, so the strength of the interaction. And it has 3 group theory indices. So you're not surprised that it's proportional to the structure constant FABC. This term came from, for example, the expansion of F mu nu squared, where you have 3 A's. So you had an A mu, so what was it? It was an A mu, sorry, no, it was a D mu A nu contracted with an A mu A nu. Okay, that came in the expansion of the kinetic term, that F squared term. And there was an FABC multiplying the A mu A nu in F mu nu A. And there was 1 power of momentum appearing in this vertex because there was 1 derivative in that interaction term. And so here, I'm just going to write down 1 representative term here. So I'm not going to, the calculation would take a couple weeks probably, at least a week or 2, if I kept track of every single goddamn term in the calculation of the beta function. So I'll just be a little more schematic when I show you how the computation works. So here you can see this also has 3 Lorentz indices, 1 momentum down here. And finally we have the 4-point interaction, reflecting the fact that gauge bosons can bounce off of one another. This now has 4 Lorentz indices and 4 group theory indices. And it's proportional to g squared because it came from the expansion of F mu nu squared, where both of the F mu nu's, so F mu nu was the usual electromagnetic kinetic term plus g times FABC, A mu B, A nu C. So this is the term of order g squared in that expansion. So it has 2 powers of the fine structure constant. And then it will have some Lorentz indices that come from the various ways that those A's can be contracted with one another. And so one does have to be a little careful with how these various Lorentz indices and group theory indices are arranged with respect to one another. So here, A, B, C, and D are the free indices, and you can see this term here is the one where so here you can see that the A and B are paired up, and the C and D are paired up. And then, so this A and this B are paired up, and then that mu and that rho are paired up, and the nu and the sigma are paired up. And then there's another term, so here I'll just write out that next term for you explicitly. There's a next term where the mu pairs up with the sigma, and the nu pairs up with the rho. And then there are various other terms that appear. So for example, you have to pair that A index up with the C guy, and then talk about the various different ways that those Lorentz terms appear. And you get a total of 6 different terms here with various signs. You can see pretty quickly why it is that these Yang-Mills scattering calculations can get pretty complicated pretty quickly. Now, in the gauge fixing procedure, we discovered that there has to be a ghost field represented by a dotted line. This ghost field, there are d species of ghost fields, so 8 in the case of SU3, because there are 8 gauge bosons, and that group theory index A runs from 1 up to 8. So these are anti-commuting scalar fields, and their kinetic term is quite simple. We worked it out last time. It's just the kinetic term for a scalar field with a delta AB. And the interesting term is the interaction term, so which is how the ghost fields give us some sort of non-trivial answer or non-trivial contribution to the one-loop determinant that depends on A. So this has an A, B, and C index, so you're not surprised if it's proportional to F, A, B, C. And it has a mu index, and that reflects the fact that in the coupling between the ghosts and the gauge field, it was gauge field times ghost derivative of ghost. So you have to have one of the momenta here. So, for example, the way that we wrote out the ghost interaction term, I believe we had the derivative acting on the C bar. So that means that you have the final state ghost field, so you pull down a factor of Q mu. Of course, we could have integrated that term by parts, and then you would have some different momenta that are appearing. Good. One of the things to keep in mind is that these scalars are anti-commuting, so every time you do a loop of a ghost scalar, you have a minus sign associated with that. And that's very important. That's crucially important. And indeed, that is a vital ingredient in the computation of the beta function. And finally, we have the fermions. So just to make life easy, I'm not going to write out the Dirac index explicitly. And in fact, whenever I can get away with it, I may not even write out the representation theory index. So here I runs from 1 up to the dimension of the representation R that the fermions transform in. So there's a 3-point, oh, I'm sorry, let me write the propagator first. So there's a propagator, which is just the standard propagator for a Dirac field. So it's 1 over p slash minus m, or sometimes we write it as p slash plus m over p squared minus m squared. And I'm being a little sloppy here. I'm forgetting about all my I epsilons, but when we do loop integrals, we might have to put those back in. There's a delta ij reflecting the fact that the kinetic term doesn't change the species of the fermion. It doesn't change that representation theory index. But on the other hand, the interaction term does do something non-trivial to that representation theory index. So here we have, so this is very similar. So if we were just doing electromagnetism, this is what the coupling would look like. And now in Yang-Mills theory, we have a copy of the representation theory matrix. And so you can see that when a gauge boson couples to one of these matter fields, it acts on that species index, or that representation theory index I, in a way that I think we discussed last time. Okay, so these are the Feynman rules. You can tell by the fact that it took me 20 minutes to write down the Feynman rules that I'm not actually going to have so much time to really perform some delicate loop calculations here, and not, I think I have at least 6 or 7 Feynman diagrams that I'd have to write down and calculate in order to compute the beta function. So I'm just going to give you a more schematic overview and pay special attention to how the group theory indices behave, because that's the new ingredient relative to the one-loop computations we already did in QED. But before I start getting into this, let me just pause here and see if there are any questions. Everyone's clear? I mean, there's like about 3 or 4 different types of index floating around here, so everyone's clear on which index is which? Yes?
Like, let's say I and J, would be like up and down quark, for example?
No, I and J label the different color of the quark.
The color
Okay.
of the quark.
So I and J. So in the case of QCD, I and J label the different colors of the quark. So So there's three possible colors corresponding to the fact that the quarks live in the three-dimensional representation of SU3, the fundamental representation of SU3. The up and down, that's this, well, sometimes we call it a flavor index. That's reflecting, that's this NF here. Okay. So NF is counting the different numbers of species of quark. I should be careful. I use the word, I've been using the word species loosely. Usually when we have multiple different kinds of particle that are identical, we call them different species of the same particle. Well, they may or may not be identical, but sometimes they are. And so I've been a little sloppy in that sometimes I've called I and J a species index, and sometimes we might refer to an index that tells you whether a quark is up or down or strange or charmed or whatever as a species index. So I'll try and be a little more precise and refer to I and J as the representation index. So that would be the color index of the quark. And I'm actually not in this class ever going to write down an index that runs over the flavors or the different number of species of quark. Sometimes people also call that a flavor index. There's lots of different, there's colors, there's flavors, there's all kinds of good stuff here. Good. Yeah. So this is the representation theory index. Now, I'm not strictly speaking proceeding historically because I haven't actually motivated or introduced to you the theory of QCD and why there are three colors as opposed to other sorts of colors. I mean, that would be a long story that would take us through a lot of very interesting history and a lot of very interesting developments. Instead, I'm proceeding somewhat ahistorically. I'm just declaring that this is Yang-Mills theory and this is what the theory is. And then by the end of the semester, we'll have about 2 weeks when we can discuss in a little bit more detail what the motivation is behind the particular matter content of the standard model that we observe in nature. Okay. Good. So we'll get some understanding for why it is, we have three generations, so we have three colors, and, well, I don't know how much detail I'll get into, but we'll try and develop a little bit of understanding for how the matter content of the standard model is constrained. So for example, next week, Guy is going to give you a lecture on anomalies. That's one of the most powerful ways we have of understanding why the matter content of the standard model has the form it does. And actually, at the end of class today, hopefully I'll have time to discuss grand unification, which is another sort of very strong hint for how it is we know, or one of the reasons we suspect that is responsible for the origin of the particular matter content of the standard model. That is to say, the particular choices of representations and the types of particles in different species that appear in the standard model. Good. If that's not clear, hopefully it'll gradually become clear. Or maybe not. We'll see. Good. Any other questions? Yes?
So say we wanted to include neutrinos or something.
Uh-huh.
Would there be, in the neutrino propagator, would that be off diagonal in the I and J?
Yes, absolutely, absolutely.
Yeah,
Well,
okay.
so in the so I and J here is a color index in the case of SU3. So the neutrinos don't actually carry color charge, but they do carry other sorts of charges. And in the neutrino case, for example, if you have multiple species of particle, it might be that there's the kinetic term, the derivative term is diagonal, but the mass term is actually a matrix. So for example, that's indeed how the neutrinos behave. For the neutrinos, schematically, you have something like psi I d slash delta ij plus some non-trivial matrix mij. So that's roughly speaking what the kinetic term for a neutrino looks like. Okay? Where that matrix mij is not diagonal. Good. Yeah. But that's probably beyond the scope of what we'll be doing in this class. Any other questions? Good question. Now, as an exercise for yourself, you could convince yourself that in the case where I and J is a representation theory index, you could not write down such a term and still have a gauge invariant action. So if that's not obvious, prove it. Okay? See what would happen if you tried to write down such a term where I and J is a group theory index. In the case of neutrinos, it's not a group theory index. It's one of these so-called flavor indices that labels the different species of neutrino. Okay, so there's 3 species of neutrino, so that was some 3 by 3 matrix. Yes. Okay, good. Okay, but back to the beta function. So the Lagrangian of the theory, if we write it in terms of the renormalized fields rather than the bare fields, well, as we introduced last time, there are a bunch of wave function or normalization factors that we called Z2 and Z3 for the matter field and the gauge field wave function renormalizations in particular. And then there was a coupling constant renormalization that we called Z1. So this is what the action looked like. And here I've suppressed an I and J index, so if you wanted to, you could put in that representation index there if you like. And I've written here only one representation R, but I could add multiple copies of this if I wanted to have, to reflect the fact that I have NF fermions rather than just one fermion. But for the sake of keeping life simple, I'll just restrict myself to one fermion. And in fact, it's a true statement, and as we go through the computation, I'll invite you to check this yourselves in your heads, that all of the different species of fermion will have the same wave function normalization factor Z2. They're indistinguishable, their interactions are the same, so the one loop computation we're going to do will be the same for each fermion. Good. Now what is the idea? The idea is that if you wrote everything in terms of bare couplings, so this term here, G times Z1, is related to a bare coupling that appears in the action when written in terms of bare fields. So G times Z1 divided by some appropriate wave function renormalization factors that reflect the fact that there's one gauge field, so 1 power of the square root of Z3, and 2 fermions, all has to be equal to the bare coupling constant G0. And if you want to understand the dependence of this on renormalization group scale, you just remember that G0 is the actual parameter appearing in the action. So this is the guy that is independent of the RG scale. So that means that if you want to write down the beta function for the coupling, you just take the derivative of both sides of this equation with respect to mu, and you get that the beta function for the coupling, which is d coupling by d log RG scale, what is that? Well, that's just the derivative with respect to the log of the RG scale of, well, I'll just write that as Z2 plus 1/2 Z3 minus Z1. Any questions on that so far? Good. And so this is the quantity that we're going to compute. And what is this going to depend on? This will depend on, well, it'll depend on the coupling constant G, of course. It'll be some power series expansion in G, of which we'll only compute the leading term. It will depend on our choice of representation R for the matter fields, the number of matter fields, as well as, of course, the choice of gauge group G. And in particular, what we're going to find is that it depends only on some of the data associated with this representation R that you learned about last week when Richard gave a substitute lecture. So in particular, what's the data that it's going to depend on? Well, it's going to depend on some numbers, and you saw that associated with the representation R, there are in particular 2 numbers referred to as T of R and C of R, let's see, delta AB. So for a given representation, if T sub R is the matrix in that representation, then the trace of TATB is proportional to the identity matrix with a constant of proportionality that is called T of R. It depends on the representation. So, for example, for SUN, T of the fundamental representation, that is the N of SUN, was equal to 1/2. And the other number associated with a representation is the quadratic Casimir. So that's what you get if you take all of the T matrices and you square them and sum over A. You get something, again, proportional to the identity matrix, now acting on this representation theory index, with a constant that's called the quadratic Casimir C that depends on the representation. So, for example, I think on the problems that you turned in Tuesday, I probably asked you to compute these numbers for the three-dimensional representation of SU3. And I'll be using those results later today when I do the beta function, if I ever get there. Questions? Good. So to do this computation, what we'll do is we'll use dimensional regularization. So we'll be working in D is equal to 4 minus epsilon dimensions. And we'll compute Z1, Z2, and Z3, or we'll sketch a computation of Z1, Z2, and Z3. And we have to remember that epsilon here, if you think about it in terms of a cutoff scale, goes like the log of the cutoff scale. So that means that to calculate the logarithmic derivative of Z1, Z2, Z3, we need to find the cutoff dependence of these objects. As in the case of QED, dimensional regularization is much nicer than, say, a hard cutoff regularization because it preserves both Lorentz symmetry as well as gauge invariance in the intermediate stages of the calculation. Okay, so let's just go through one of these calculations in a little bit more detail and remind ourselves of how it works. So let's focus on Z2. Okay, that's the easiest one. That's the wave function or normalization of the fermions. So how do we go about computing a fermion propagator, of the fermion wave function or normalization? Well, you start with the fermion propagator, which is given by its tree level result, plus a one-loop result. So that's the one-loop contribution, plus a counter term that we usually draw with a little x, or an x with a circle around it, plus terms that are higher order in perturbation theory. And then we could rewrite this. And here, of course, I'm trying to make my notation compact, so I'm suppressing a representation index. I should really call that an Sij, and put i's and j's on the endpoints of this diagram. But and I guess we'll do that in a second. But right now I'm just being a little bit more schematic. And the idea is that, as we saw in the case of QED, and even in the case of the scalar field, this will resum into 1 over p slash minus m plus sigma, where sigma is the thing that you get when you only include all of the connected diagrams. So you have this one loop piece, which we write like that, plus the various counter terms. And what are those counter terms? Well, there's two different types of counter term. So there's the Z2, so there's the counter term that comes from here. Okay, there's this counter term. So you write Z2 as 1 plus delta, where delta is your counter term. And you have a momentum here. So the Z2 gave us a contribution that looks like the counter term delta 2 times p slash, because of that d slash in the action. And that's where that factor of I came, because d slash is IP. And then there was, for example, a mass renormalization plus higher order terms. And we're not interested in that mass renormalization. We're only interested in Z2. So this here is the term that we want. Now in QED, how did this computation go? So this is a computation that we did. So I'll just remind you of the answer. So in QED, you do this computation, and, well, the sunset diagram, which is often what this is called. So the sunset diagram, well, it's proportional to the electric charge squared with some constant of proportionality that we actually computed. There was some 8 pi squared. And it has a UV divergence that looks like 1 over epsilon, plus various terms that are finite that we're not going to care about. Because the point is that the wave function or normalization is designed to cancel this 1 over epsilon. So Z2 minus 1 is then going to be proportional to, well, there's a minus sign to cancel that epsilon, e squared over 8 pi squared times 1 over epsilon. And then you could also add finite terms to this counter term depending on what regularization, what subtraction scheme you're using. So for example, in dimreg you have these Euler-Macaroni constants that appear here, and then in the minimal subtraction bar scheme you add those constant terms as well to the counter term. This just corresponds to a slightly different way of defining your renormalization scheme. But of course, we only care about that leading 1 over epsilon piece, because we want to take d by d log mu, and epsilon goes like log mu. Good. Okay, so is this more or less familiar to everyone? I mean, you've done this calculation before, so I'm not going to do it. I'm not going to go through and do it for you again in Yang-Mills theory, because you've already done it in both scalar field theory and in QED. And so I just want to point out how this calculation changes in Yang-Mills theory. So in Yang-Mills theory, we now have the sunset diagram where we now have a few other representation theory indices floating around. So here now we have the I and J representation theory indices. So you'll get a factor of the representation matrix TA here. So I guess strictly, so you could say that there's an index mu A for that gauge field that you're integrating over. But of course, I mean, those mu and A indices are going to get contracted in the final answer, so they won't appear in the final answer. So you'll get another representation theory matrix TB for that other interaction. But of course, this gauge boson propagator has a delta AB in it, so you actually get a TA, TA. And so if you want to be a little bit more explicit, we should have a representation theory index L for that internal propagator, and this would be TAIL and TBLJ. So when you sum over L's, you end up computing the matrix product of TA with TA, and this has to depend on those external representation theory indices ij. So what you're left with is the ij component of t squared. Is that more or less clear? Less clear? Are there any questions on this? So if you just stare at these Feynman rules that we wrote down, okay, where's the Feynman rule? You stare at this Feynman rule. All I'm doing is I'm putting in that object there. I'm not writing the gamma matrix explicitly because that part of the computation follows through exactly in QED. I only want to tell you what the new ingredient is. you have those gamma matrices, and you had a G mu nu coming from that gauge boson propagator, so you'd get a trace of gamma squared with the traces over the Dirac index. But now here you see you also get some fun and games going on in the group theory index. If I wanted to, I could be a little bit more specific, so you get 2 powers of the gauge coupling, one for each vertex. And you have, you have these other terms that are, the 1 over 8 pi squared, which is exactly the same as you had in the QED case, along with a 1 over epsilon. Okay. So all I'm doing is trusting you to remember more or less how the QED calculation went, and we're seeing that all you do is you replace this E here, this which was the QED coupling, by this fancier coupling in Yang-Mills theory. And the point is that we've already given a name to this object, which is TATA summed over A. In particular, it's the quadratic Casimir. And if you want, we could remind ourselves that we could write out the group theory, the representation theory index delta ij. So what does that mean? That means that in Yang-Mills theory, Z2 minus 1 is given by the same thing it is in QED, except there's one small modification that reflects the fact that we're now in a non-abelian gauge theory. So that E squared gets replaced by G squared times the quadratic Casimir. So this is a leading term at order G squared, but of course there are going to be higher order terms at order G to the 4th, and so on. Is that more or less clear? I mean, I don't want to go through the whole Feynman calculation again, because I feel like at this point you guys are experts in that. So that's the calculation of Z2. And I'd just like to rather quickly sketch out how the calculation proceeds for the other 2 wave function normalizations. Okay. So in fact, these are also just going to be very, I don't want to say very, somewhat straightforward generalizations of calculations that we've already done in QED. So for example, if you want to calculate Z1, Z1 was the coupling constant normalization. And so remember the coupling constant is, so the coupling constant, we sometimes represented it like this in electromagnetism. So this would be something like, so in electromagnetism, we called this IE gamma mu. And then this was equal to, well, the tree level coupling plus the higher loop couplings. So in the case of electromagnetism, the only one loop contribution, which is the one that gave us the anomalous magnetic moment of the electron, oops, sorry, wrong diagram, was the one that looked like this. Okay. But if you think about it, in Yang-Mills theory, there's actually one additional contribution to the fermion gauge boson coupling, which arises because gauge bosons can now interact with one another. And then, of course, we have to add the counter term. And then there are terms that are higher order in the coupling that we won't be discussing today. Everything clear so far? Good. Now, how did this work in QED? So in QED, we just had the second diagram. Yes?
so these are all third order, the second two diagrams are third order in the Coupling process?
Yes.
So then what about the diagram that has that has a fermion, a gluon coming off the bottom, and a gluon loop stuck on the side?
Yes. So remember, so that's not a 1pi diagram. So remember, we only want to include one. So that diagram has the property that if you cut it, it falls into two diagrams. So that's not 1pi. Another way of saying that is that if we worked with the one-loop corrected gauge boson propagator instead of the free propagator in Feynman diagrams, that would effectively be including that diagram. Okay, great question. Good. Everyone understands. Everyone understands that. Good. Good question. Good. So in QED, we just had the second diagram. And we studied its one-loop divergence, and indeed, we had to compute Z1 because that was the counter term that we needed to fix in order to determine the anomalous magnetic moment of the electron. So I'll just tell you what the answer was. So Z1, so I guess rewrite it. Z1 minus 1 is minus, well, it's going to go like E cubed. Actually, I need to be, sorry, we need to be a little bit more specific. It goes like E squared, but because remember, when we define Z1, there's an explicit power of the coupling constant out front. So the total diagram goes like E cubed, so Z1 goes like E squared. So Z1 was E squared over 8 pi. There's that combination of E and pi again, times 1 over epsilon. And just as in the case of Z2, there's going to be some relatively simple modification of this to take into account, in Yang-Mills theory, to take into account the fact that we have some group theory indices flying around. So what do the group theory indices look like? So in Yang-Mills theory, what is the diagram we're talking about? Well, here's the diagram. So if we want to write out the indices a little bit more explicitly, we have an I index here and a J index here, and a free mu and an A index. And what will the group theory indices look like? Well, you'll get a G cubed because there are 3 interaction vertices, and you have to have 3 powers of that representation matrix T. And so we could just call this matrix, so there's going to be some group theory index here associated with that interaction vertex. And because the propagator here, it's proportional to a delta function on the group theory indices, those have to be the same group theory index. And, well, you could have a representation theory index L here and K here. And, well, that'll be a TA index. So what you'll get is TB IL times TA LK times TB KJ. And when you contract up those representation theory indices, all you're doing is multiplying those matrices together. Now this is a slightly more complicated group theory object. It's cubic in the generators rather than quadratic. But as I promised you earlier, this can still be written relatively simply in terms of the sort of fundamental constants, the quadratic Casimir C and that trace constant T. So to see how that goes, let's just go through that exercise a little bit. It's sort of instructive. So let me just rewrite this as TB times TB TA plus I FABC TC, just using the fact that when I commute 2 elements, I have to pick up the structure constant, the commutator. So what is that first term? Well, that's TB summed over B times TA. So that's just what we call the quadratic Casimir times TA. Okay, that one was easy. And then let me rewrite that second term a little bit. So that's plus 1/2 I FABC times the commutator of TB with TC. Using the fact that FABC is antisymmetric, so I could rewrite FABC TBTC as 1/2 FABC times the commutator. And what is that commutator? Well, that's going to be 1/2 I FABC. What is the commutator? It's TBC, sorry, not T, FBCD times TD. And I can now use the fact that those structure constants have a slightly different name, as you, let's see, either discovered in your last problem set or you're going to discover in your next problem set. In particular, they're the entries of the representation theory matrix in the adjoint representation. And so this, what is this? This is T, how do I want to say this? This is TA. No, let's call it, did I get my indices right? Yeah, sure, I got my indices right. This is TA BC times T, like, wait, did I get my, yeah, times TD BC times TD. So what is this? This is in the adjoint representation. So what is that? That's the trace of TA in the adjoint representation, otherwise known as T of A times the identity matrix in the adjoint representation, delta AD times TD. Okay. So what do you get? So this whole thing is C of R minus 1/2, because of that 1/2 out front, times that trace constant in the adjoint representation times TA. So here I'm using the fact that TA, well, the trace of that in the adjoint representation is the thing that we called T of A times delta AD. Did you calculate T of A in the adjoint representation in that problem set I gave you last week? If you didn't, it's reasonably straightforward. So I went through that group theory nonsense a little bit quickly. Promise me there's nothing non-trivial going on here. I'm just mucking around with the indices. If that was a little too fast, then I invite you to go through it all again yourselves. I was a little fast about the factor of I and stuff like that. But is the general idea clear? Is everyone clear on the general idea? Okay, so what do we see? So we see that in Yang-Mills theory, when you calculate Z1, you just get the same answer that you did in Z1. All of the spinor indices and stuff like that just is exactly the same, except that E squared gets replaced by the coupling constant squared divided by 8 pi squared times this particular combination of data that depends both on the gauge group and the representation. Now, as we saw above, in Yang-Mills theory, there's also the contribution from the new diagram that doesn't appear in QED. So what does that contribution look like? So it looks like that one. So let's not, I don't want to bother going through all of the Feynman diagram calculation. You could do it yourself. You could look it up in any of the textbooks if you wanted to. It's just another loop calculation with a bunch of indices like you've already done. I'll just pay attention to the group theory indices since they're sort of interesting. It's sort of interesting to see how those group theory indices play with one another. So here, let's call the index for that gauge boson A, and let's call this one B and this one C. So you'll get an FABC coming from this interaction vertex right there, and then you'll get a TB and a TC from those interaction vertices with the fermions. And again, I guess I could write an I and a J index here and an L index there, and that L index just tells us to multiply the TB and TCs together and take the IJ component. And what is that guy? Well, again, we can use the fact that FABC is antisymmetric, so this is proportional to FABC times the commutator of TBTC, which is FBCD, which, as we saw, is the trace in the adjoint representation of TATD, otherwise known as TA times delta, TD, yeah, good. Otherwise known as delta AD times TD, so you get TA there. So again, this will give you a contribution to the interaction vertex that's proportional to TA. So the total contribution is given by this answer here. So this was from this diagram that we were already familiar with from QED, plus a correction to this coefficient right here. So the total answer, I'll just tell you the answer so that you don't have to, so that we don't have to go through and keep track of all those numerical factors ourselves. Well, it'll be some linear combination of CR and TA. Good. Any questions? There's a lot of signs to keep track of, a lot of numerical factors to keep track of in this calculation. Quite famously, the first time this calculation was ever done, the signs were not kept track of carefully, and the first people to do this calculation got the wrong sign for the beta function. There's some interesting history associated with that, which we don't need to go into, but, if you made a sign mistake in these calculations, you would be in very good company. Finally, let me just very schematically sketch the computation for Z3. Z3 is, of course, the most interesting and non-trivial calculation. So Z3 was the wave function renormalization of the gluon. So there's lots of stuff to worry about here. So we need to calculate the corrections to the propagator of the gluon. So there's that one diagram coming from the quartic interaction, another coming from the cubic interaction. We also have the ghost interaction with an important minus sign because the ghosts are anti-commuting scalars. And then we have the contribution from the fermions. And finally, all of that will have a divergence at one loop that has to be canceled by a counter term. And that counter term gives us the desired renormalization scale dependence of Z3. Sorry, I guess. Is it Z3? I forget. Yeah, Z3. Okay. So, just very schematically, if you did this, you would get an answer which, well, is proportional to a function that in QED we called pi of k squared times k squared g mu nu minus k mu k nu. The only difference with QED is that we now have an additional group theory index to keep track of. Okay, so for example, if there's an A and a B index at each endpoint, and it's a somewhat tedious but straightforward exercise to go through and calculate all of these things explicitly. So, for example, it turns out that the first diagram is actually 0. That's not entirely obvious. You actually have to do the calculation. It turns out when you do it, you can actually use the symmetry. You end up with Euclidean. You end up with a four momentum integral as usual, and then you can use the parity prop. You end up with a four momentum of something that's odd, and so it actually vanishes by parity. The other terms are non-trivial. So, for example, what does this term look like? Well, this term will be proportional. Well, in fact, it's very similar to the calculation we did above. You'll get 2 powers of f, 1 power from this interaction vertex, 1 power from this interaction vertex. That'll be contracted together. So just as in this calculation right here, where you had 2 powers of f that are contracted together, you'll get something proportional to T of A. Whereas when we do the ghost field, well, the ghost field also transforms in the adjoint. That coupling is also proportional to FA, BC for each one of those interaction vertices. So you'll also get something proportional to T of A. Okay. And I guess I should say there's a delta AD here, a delta AB here, because there are free group theory indices. And then finally the contribution from this guy. Well, let's see if anyone is paying attention. Anyone sufficiently awake enough to guess what that answer is going to be? Okay.
G squared is
Well, yes, there's a G squared. Okay, good. Any other guesses? There's 2 factors. First of all, what's the group theory dependence? Well, this was a T of A because you had the adjoint running around in that representation. So this is going to be a T of R because you have an adjoint running around in the middle there. If that's not clear, let's just go through it. So you're going to get a T sub A coming from this vertex, a T sub B coming from this vertex, and then because you sum over all of the fermions running around in the loop, you have to take the trace over the INJ. You get a trace TATB, otherwise known as T of R times delta AB. And then there's one other factor that's missing. Remember, we have to sum over all the fermions running around the loop. Well, okay, I'm not smart enough to keep track of the signs. But aside from the minus sign, possibly, there's one other factor missing. We have NF species of fermion, and so you have to do this one loop contribution to the gauge boson propagator for each one of the fermions. So you get a total NF out here. So if you put all of this together, I'll just quote the answer for you. The gauge boson wave function renormalization counter term has one term. So, well, again, it's a G squared over 8 pi squared. And there's 2 different types of contribution. So you get a 5/3 times T of A minus 4/3 times NF T of R. So the NF T of R comes from this term, and the T of A contribution comes from the ghost and the gauge boson. Good. Everything clear so far? So this is the hard part of the calculation. Now we're going to get to the fun part. But before I get to the fun part, I just want to make sure that everyone's following me so far. Okay. So let's put this all together. So remember that the beta function, what was the beta function? Let's just remind ourselves. So here's the beta function. It was proportional to the logarithmic derivative of z2 plus 1/2 z3 minus z1. And we use the fact that epsilon is like 1 over epsilon is like log mu. So this beta function is proportional to, well, what do you get? You get g squared. Actually, we need to be a little more careful. I forget a factor of g. Okay, I may have forgotten a factor of g somewhere. If that is the case, I'm going to discover it very quickly. Okay. Because I believe there's a g, that's a g cubed. Hang on, let's think about it. Okay, my apologies. Yeah. I think I left out an overall factor out front. There's like a factor of 1/2. Okay, my apologies. So, beta function for g is like g squared? Okay. Well, let's see what happens. So the beta, sorry about that. So the beta function, unless we may discover that I've lost a factor of g somewhere. But the beta function, as I've computed it, is proportional to g squared with some numerical coefficient times some linear combination of TA, TR, and C. But the important thing to note, one of the interesting things to note, is that we have a C here, so Z1 was proportional to minus C. And where was it? Z2 was also proportional to minus C. And the beta function is proportional to Z1 minus Z2. So those factors of C all cancel. So the beta function is proportional to only TA and TR. And so you can see here that something very interesting is happening. The beta function will be positive or negative depending on NF. Okay. And there's actually an overall minus sign out front. Sorry about that. So in particular, for QCD, well, the quarks are in the fundamental representation. So T of R is equal to 1/2. And T of A, I guess you didn't compute it, but it's straightforward to compute. Maybe Richard computed it for you. Is equal to 3. And so the beta function is equal to minus g squared over 16 pi squared, just inputting those numbers. 11 minus 2/3 times the number of species of quark. Okay. So if the number of species of quark is less than 16, so this was for SU3, that implies that the beta function is negative when G is small. Of course, when G is large, the higher order corrections to this beta function will be out of control. So what does this mean? What this means is that if G starts out small so that you can trust this formula, as you go to higher and higher energies, G just gets smaller and smaller and smaller. So this is asymptotic freedom. The coupling constant in QCD, because there are less than 16 species of quark, goes to 0 at high energies. We should contrast this to the behavior in electromagnetism. In electromagnetism, remember that because of screening, the effective electric charge of something with fixed bare charge got smaller at long distances, so it gets stronger at short distances, at high energies. And in particular, the effective coupling constant, the electric charge, went to infinity at high energies. So this is what was known as a Landau pole. And this reflected the fact that quantum electrodynamics, because of this Landau pole, is not a theory that is well defined at arbitrarily high energies. So QED is just not well defined at very short distances. It works fine as an effective field theory. In fact, at very low energies, it works very, very well. You know, for our current world, at very low energies, the coupling constant in QED is small. The fine structure constant is, about 1%. So we can do Feynman diagram calculations, compute things in QED at very high order using perturbative techniques. But quantum electrodynamics at a fundamental level, because of this Landau pole, is just not a well-defined theory at arbitrarily short distances. In fact, Yang-Mills theories are the only asymptotically free four-dimensional theories. So the only quantum field theories of particles with spin less than or equal to 1, as far as we know, that can be defined at arbitrarily short distances are Yang-Mills theories. And in particular, unlike electrodynamics in QED, where perturbation theory is good at low energies but fails at high energies, in QCD, for example, perturbation theory is great at high energies, but it fails at low energies. That's why you can take classes in electrodynamics, and it's very easy to study, and you can understand electrodynamics, as a freshman, okay? But you can't understand, that's why the behavior of the nuclear force, for example, is very counterintuitive. And that's why, for example, quarks at very long distances don't obey Coulomb's law. They don't obey Coulomb's law because Coulomb's law is a feature of electromagnetism at very weak coupling. At very strong coupling, quarks obey something else. What they obey is much more complicated, and you'll learn a little bit about it next week. Let me pause here and see if there are any questions. This is really one of the punchlines for this course. I have a few minutes left, so I thought what I might want to do is show you one sort of exciting consequence of this reasoning for some speculative ideas about particle physics. But before I do so, let me just pause and see if there's some questions. Yes?
Is the electroweak theory asymptotically free? Or
Yes.
is it the same Landau pole?
The electroweak theory is asymptotically free. We'll see that in just. So I haven't written down, I haven't focused on electroweak theory because there's a whole new ingredient for electroweak theory called the Higgs mechanism, which we'll discuss a little later on in this course. But at very high energies, it is asymptotically free. But there's a whole other set of phenomena associated with the Higgs mechanism, which we'll get to. But yes, that's actually one of the things I'll comment on is the running of the electroweak coupling. Good. Other questions before I get into that? Okay. So, in the Standard Model, all of the forces are described by Yang-Mills fields. So you have the electroweak fields, electro standing for electromagnetism, and weak is an SU2 Yang-Mills theory. And quantum chromodynamics, the theory of the strong force, is given by an SU3 gauge theory with a particular matter content. So with various matter fields. That we'll be writing down in greater and greater accuracy over the next couple of weeks. So there's a few more things that we'll have to learn in order to write down these. So it turns out that there's also a scalar field, and the Higgs field that couples to the electroweak sector in an interesting way. We also, unfortunately, are going to need to deal with the fact that so far, whenever we've talked about fermions in this class, we've talked about Dirac fermions, 4-component fermions. But as you may or may not remember from our discussion of spinors, you can also talk about 2-component Weyl fermions. So Dirac fermions are parity symmetric, whereas Weyl fermions carry handedness. They're either left or right-handed. It turns out that the Standard Model of particle physics is not parity invariant. So left-handed particles have very different interactions from right-handed particles. Okay. So when we write down the Lagrangian of the Standard Model, we're going to have to first remind ourselves a little bit about chirality and all of that stuff. But just as a bit of a preview, let me just tell you that we're going to write down the matter content. And given everything that I've told you today, you can work out the running of the gauge couplings of the Standard Model. And when you do that, you get something very interesting. I think, and this is a speculative idea, but I think it's one of the most influential and important ideas in particle physics. So in order for me to explain this, what I want to do is work not in terms of the coupling, but in terms of the inverse 1 over the square of the coupling. So in particular, let's let alpha be the square of the coupling. Okay, I'm going to be a little schematic. I'll leave out all of my various factors so that, yeah, this is where the fact that I think I should have gotten a g cubed instead of a g squared is going to haunt me. It is a g cubed. So I missed a factor of g somewhere. I'm probably just being stupid. I probably absorbed it into one of the definitions. Okay. But what we saw is that the beta function, see, I knew I need to not write my notes late at night. So the beta function for the coupling, what was it? Well, it was some constant, and it's times g cubed. Okay. So you'll trust me, it's times g cubed. Sorry, I missed a factor of g somewhere. Let's not hunt it down. I only have 4 minutes left. So if we define alpha to be the square of the coupling constant, then that implies that beta alpha, which is the derivative of alpha with respect to log mu, what is it? That's g times the beta function for g. So that's going to be some constant times g to the 4th, or a constant times alpha squared. So then, if you want to study the beta function for alpha inverse, so the derivative of alpha inverse with respect to log mu, what is that? That's 1 over alpha squared times the beta function for alpha, which was c times alpha squared. So that's just a constant. Okay. So what does this mean? Okay, why did I go through and do this? This means that if we write alpha inverse, which is 1 over the coupling squared, then its beta function is a constant. So that runs linearly with energy. So if the coupling is small, that is to say, if alpha inverse is large. So all I'm using is the fact that because my beta function is modulo some errors that I made proportional to coupling cubed, that means that the differential equation that the coupling obeys with energy, dg by d log mu, is proportional to g cubed. That has some complicated solution that I would have to think about to write down because I can't solve differential equations. But if I work in terms of 1 over coupling squared, I find that the derivative of that is a constant. That's a differential equation even I can solve. Okay, it just says that the running is linear. So that means, for example, that if you want to study the change of the couplings with energy, so I'll work on a logarithmic scale, so the lower scale will be energy, and it'll be logarithmic. So for example, this would be, say, 10 GeV, and then we would have 100 GeV, so on and so forth. And then here, this is the coupling constant. So for QCD, the coupling constant, well, 1 over the coupling constant squared, along with some factors of 8 pi and stuff that I haven't bothered to write down, is about 10 at 10 GeV. And we've seen that the coupling constant decreases at high energy, which means the inverse coupling constant squared increases. And because the beta function for alpha inverse is a constant, it's going to increase linearly. So that means that you're going to have some curve like that. So remember, we're talking about the inverse coupling constant here. So when the coupling constant goes up, that's good. The theory is becoming more and more weakly coupled. So that is the coupling constant for the strong force. You could also do the coupling constant for SU2. So we might call this alpha 3. It's alpha strong. This is the coupling constant for SU2. Alpha 2. Okay. It's also linear. It has a different slope. 2 lines with different slopes are going to intersect. Okay. That's, I don't know, Euclid, I suppose. And then, well, I didn't draw this very well. Here, let me redraw this so that it'll all fit a little bit better. So let's draw this like that. So then we have that. Still not very good. God damn it. Okay. Yeah. Well, so this is going to be the U1 coupling of electromagnetism, basically. Now, because U1 has a Landau pole, it runs strong at high energy, so that means that the slope of this straight line is going to be negative. And it turns out that the straight line looks a little bit like that. Okay. And the slopes of these lines, so the value, so what is the data that's going into these graphs? The slopes of these lines are determined by the matter content of the standard model, the number of particles that we have, what representations of the gauge groups we have. And the values of these intercepts here are just measured values of the coupling constants. So for example, this coupling constant here, that's the fine structure constant, 1 over 137. Okay. So that's 137. Although I've run it up to 10 GeV, so it's actually a little less than 1 over 137. I think it's like 60 or something like that. So you can see that a miracle has almost occurred here. So 2 lines intersecting surprises nobody. Okay. 3 lines intersecting, well, okay, now you're talking. So it turns out that with a minor modification, well, with a minor modification of our theory, these lines will intersect. So they almost intersect. And what is the energy scale where they almost intersect? We actually have to put in data there, see what it is. Yeah, they almost intersect at about 10 to the 16 GeV. Okay. And so the scale at which they intersect is called the grand unification scale. And it's about 10 to the 16 GeV. So why is it interesting if those coupling constants intersect? Well, one of the things that you may have noticed about Yang-Mills theory is that it has one coupling constant, G. So if you have an SU2 Yang-Mills theory that has a coupling constant, G2, and an SU3 Yang-Mills theory that has a coupling constant, G3, those coupling constants are different. At low energies, we look at those coupling constants, they're different. But if at very high energies they happen to be the same, that means that that SU2 and SU3 could be part of some larger gauge group. So the history of physics is sort of one of unification, electricity and magnetism unified with each other, and then unified with the electroweak theory, with the SU2 weak theory. And so one of the most compelling ideas, I think, in quantum, in particle physics, is that all of the fundamental forces together unify with one another in some way. And the fact that these three lines just about meet has been taken as evidence for this idea that, in fact, all three of these gauge fields are, in fact, just different low-energy manifestations of one more fundamental gauge field. Okay. So in the simplest model, which is that proposed by Georgi and Glashow, the SU2 times U1 times SU3, they all get unified into one glorious SU5 gauge theory. There are other competing models. You know, I actually sort of am particularly fond of an SO10 model because I think it makes the matter content of the standard model look very simple. But there are various different models sort of for the potential unification of these gauge fields. I should make two other comments here. One is that I said with a minor modification, and so there is some degree of debate as to what that modification should be. So for example, it turns out that if you postulate another symmetry of nature in addition to Lorentz symmetry called supersymmetry, then automatically that makes these lines intersect. So that didn't have to happen. That's one possible way that these lines could intersect. Another way that you could get these lines to intersect is you could say, well, I determined the slopes of these lines by having using the matter content of the standard model. But what if up at, you know, a TeV or, you know, 10 TeV or 100 TeV, there's some other kind of matter content that's invisible to us at low energy because it's very massive? What would happen? Well, that would change the slope of this curve. So for example, if you had some other matter content, it might be that alpha 3 ran like that up to some energy scale, and then above that energy scale the slope changed. And so it moved the curve up. So a favorite game among particle physicists is coming up with your favorite sort of matter that you might add at the TeV scale, observing that it makes the gauge coupling constants unify, and then predicting that we'll observe this at the LHC. Okay, so that's, you know, that's a good algorithm for writing papers. The final comment that I'll make is that there's one force that hasn't been included here, which is the force of gravity. And gravity has a coupling constant. It's Newton's constant. And the scale at which gravitational effects become important is quite close to the grand unification scale. It's within an order of magnitude or two of the grand unification scale. And so in the various models that people consider, people also even consider including gravity in this story. Okay? Gravity is much harder to study. General relativity is much harder to study as a quantum field theory. It's a non-normalizable theory. As we've learned, that's not the end of the world. It just means that gravity is good as an effective field theory, but can't be defined at arbitrarily high energies. So people also try and come up with theories of gravity at very high energies and try and unify them with these gauge couplings. That's a much more speculative subject, but also a very interesting one. But typically when people talk about grand unified theories, typically what they mean are the unification of the three forces of the Standard Model, the three Yang-Mills theories, that happens a couple of orders of magnitude below gravity. So you still have all of the forces of the Standard Model unifying together, and then a few more orders of magnitude before you get up to the scale where gravity becomes important. Okay, so all of that was a bit of an aside. I just wanted to explain this to you so that you have some sort of appreciation for why this calculation of the beta function of Yang-Mills theory is so important. So as I mentioned, next week, Guy is going to be lecturing on QCD and on chiral anomalies, and then when I get back to town, we'll be talking about Higgs mechanism, symmetry breaking, Goldstone bosons, and applications both in particle physics and hopefully condensed matter physics as well. Okay, sorry for going over time a little bit. I'll see you in a week.